Hello ladies and gentlemen, thanks for tuning in again to lecture 7 today, which is going to be on estimation in sampling for GGS300 quantitative methods for spatial analysis. So where are we at with the course so far? The midterm exam has now been set. That needs to be completed by October the 11th. The important thing also is that there's going to be an assignment set today, and that's going to be due on October the 16th. So that's a Friday. We've now shifted to submitting the work on that day because many of you emphasised that it would be easier for you. And that's assignment 5. And that's a practical which is based on a lot of the content which we're going to go over today, but also on the lab content that I'll be putting up later. So let me know if you have any queries. Some of you have been doing a good job at reaching out to me and making use of my time on areas where you maybe are still a little bit puzzled or you have certain queries, particularly with the probability content. I know some of you were struggling with that, but you're making the right decisions if you're reaching out to me and asking for extra help, because then I know where you're at. I can advise you as to how to resolve the issues that you've got. And also, as I keep going back to the content, slowly we're going to be going through new areas each week, but it's going to be cumulative. So by the time we get to the back of the course, you're going to need all of that understanding on descriptive statistics, on probability, on confidence estimates, as we'll go over today. So please do reach out to me if you're still struggling with this content, and hopefully we can resolve that and get you back on track. Okay, so the aim of the lecture today is to go over estimation and data sampling. So we have some concepts that we need to cover first. So this relates to point or interval estimation. So what exactly is that? Well, firstly, what do we use samples for? And we've covered this in lots of the previous lectures. So for example, we sample because it's cheaper than sampling, doing a census of the full population. So if I wanted to go out and speak to every single person that lived in Fairfax County, that would take me a really long time. But actually, if I can design a sample which captures maybe just 10% of the population, then that would be a huge reduction in the amount of time and cost required for me to obtain the information that I require. So we're able to use a sample to represent the population and also then to estimate parameters of interest for the population that we need. So the mean or the variance, for example, and that can help us. We can basically use this to develop more inferential understanding of how the world works, depending on our research question. So there's a long-term quantitative purpose to doing this. So a lot of what we covered so far are just general concepts, but as we move towards the back of the course, we're going to be looking at those quantitative tests which provide us with an understanding of whether our assumptions for how the world works are true or false, based on the evidence which we've collected through that sample. That's why the sample needs to be collected in a way that isn't biased. Okay, so I mentioned previously that we have point estimation and interval estimation. Well, what are these? So point estimation, just think of this as estimating an individual value of a population parameter. Just think of it as the mean, for example, or the standard deviation. Whereas the interval estimation essentially is to estimate a range of the population. So think of this as a confidence interval, for example. And we want to be certain that the mean value that we obtain lies within a range which we specify. And that's an important concept that we're going to be covering today. It's important, though, not to mix up here point estimation as thinking of it as a spatial point. So this today is not particularly spatial, so don't think of this as a coordinate. When I say point, just think of it as a single value, which is, for example, is probably most likely going to be the mean, because that's what we're going to cover today generally. So for point estimation, a good way to estimate the population mean is via estimating the sample mean. So we covered this previously in descriptive statistics. So X bar represents the sample mean. We're then able to obtain this by basically summing up all of the xi values within our sample and then dividing it by the total number of entities within that sample. The sum of xi divided by n, that gives us the arithmetic mean of the sample. And we may also be interested in estimating the population standard deviation. And the best approach there is to carry out the standard deviation estimation for the sample. So you'll remember here that to get the sample standard deviation, we need to take the sum of squares, and then we need to divide it by the number of degrees of freedom, and then take the square root of that result. So to get the sum of squares, we're essentially saying for each individual xi value, so each value in the data that we collected, we need to subtract the mean. And then what we want to do is we want to square those values, take the sum and divide them by the number of degrees of freedom. Okay, and that provides us with the standard deviation. So none of this should be new to you. We've covered it many times. You've done assignments on it. You've also covered this in the tests, and hopefully you'll also have covered this now in the exam. So this shouldn't be new. You may also remember that there was a particular R exercise where I demonstrated how using the number of degrees of freedom, so n-1, helps to prevent bias. So this is important when you're calculating the standard deviation, because the smaller denominator helps to account for missing extreme values in a sample. Otherwise, you basically underestimate the true magnitude of that parameter. But this is particularly relevant for those smaller samples, so maybe where you have fewer than 30 individual data points. And if this is new to you, then make sure you cover back that R demo which I gave, I think it was in the third or the fourth week, which provides you with an example of what this means in reality. And I demonstrate how calculating the standard deviation in different ways, just using the number of entities in the sample or using the number of degrees of freedom, results in different values essentially. Generally, as I said, this is for where you have a small number of samples. In reality, in most of the statistical work that we do these days, given we have so much data, it's unlikely that you would have very few samples such as this, but it's important for you to know this and to learn it. Okay, interval estimation. So that was the point estimation. Now let's move on to the interval estimation component. So the question is, how close do we think our sample statistics are to the true population parameters? So we basically need to estimate the point statistic to a certain degree of confidence. So how confident are we that the value that we have is potentially representative of the population which we're trying to measure? So firstly, a confidence interval. So for a certain level of confidence, we can define this as the population statistics. We can define this interval essentially as being a range where we're fairly confident to a certain degree of confidence that the population statistics fall within it. Okay, so I hope that's clear. Let me try and explain it more, and then I'll hopefully make it clearer to you. So we're going to cover this today, how we calculate this particular statistic. The important point is that we basically say that we are able to tolerate a certain amount of error, and that's represented here as E, so the tolerable sampling error, and that's important. So we've covered the point estimate, which is the mean, for example, here, so X bar. And then what we're saying here is that the confidence interval, let's just say it's 90%, we as a consequence can accept a certain amount of error, and we're able to represent that relationship as I've done here, like this. It's basically saying that 90% of the values within our distribution are going to fall above or below this mean value. Okay, so we're going to cover this more, and we're going to go into detail about how we calculate this and why it's relevant. Before we actually get to that part, it's important for me just to go over the central limit theorem, because this very much guides our statistical approach to how we calculate some of these key metrics. So let's assume that we have a sample distribution. Let's draw a random sample of size n, and we say we're going to calculate the mean. for this distribution. And we're going to repeat the sampling process many times. So let's say we have a set of numbers and we're going to draw a set of samples repeatedly, and we're going to calculate the mean each time. Each sample statistic, basically, so each time we pull a set of mean values, that produces a distribution. Okay, so it's the distribution here of the sample mean. And that's what we essentially need to focus on when we're thinking about the central limit theorem, as I'm going to cover today. So for a population with mean mu and a standard deviation sigma, let's draw a random sample of size n. So if n is sufficiently large enough, then the distribution of the sample means is normal, even when the population is not normal. Okay, and I'm going to recap over these key points that I'm making at the end here, and then we're going to demonstrate in an R example how this actually holds up in reality, using some nice little loops demonstrating how the distribution changes based on the number of samples which you're essentially pulling from the population. And the normal distribution has a mean as so, and a standard deviation as so. Okay, so why is this relevant? Well, most populations in reality are often not normally distributed. So if you think of the income distribution that I presented in the first and second lectures, that's a classic example of how there's a very large positive skew on the amount that certain people earn, because you've got, the Bill Gates or the Jeff Bezoses of the world earning massive amounts of money, and then the majority of people probably earning a fraction of that, much less. So probably the majority of people earning under $100,000, for example, per year. And in reality, most of the distributions that I've worked with aren't normally distributed. In fact, you actually have to go to quite a large effort to correct for some of these statistical issues, so that you can actually meet those assumptions of the statistical tests, which we'll be covering later in this course. And one of those key assumptions is that the data are normally distributed. And as I'm stating here, the issue is that often that's just not the case. So regardless though of the shape of the population distribution, if you actually pull sample means, the distribution that it produces should roughly be normally distributed if the sample size is large enough. Okay, so the question obviously is, well, what's large enough? So here we're just going to assume that it's 30 samples, and we will pick this up within the R example which I'm going to give you. So essentially, a single sample can be representative of the true population, especially when you have a large sample. And since the sample distribution is normal, we can use the continuous normal distribution in order to understand the probability of certain values occurring, for example. So this is work that we did in the previous lecture, particularly how we calculate those standardized z-scores, which are measured in the number of standard deviations, and which help us to understand perhaps where new values sit in relation to the rest of the distribution. Or in this case, we can use it to express confidence intervals. So that content that I covered before was just giving you a bit of an overview of the central limit theorem. I think the important thing is that you go into the McGrew book and you look at particularly the box on the bottom of page 118, and I'll pick that up shortly, where it states the 3 different assumptions which are part of that theorem, which guide how we're able to pull sample statistics into a sample from the population, and then ideally relate them to the underlying population distribution. Okay, so let's go through some examples now, and let's demonstrate this. So we're going to do an R demo, and it's basically going to be capturing the effect that we see here. So imagine we have a uniform distribution of data points, and we pull each time we pull a sample, and we pull just one data point, we're going to end up with a set of values that essentially is very similar to the underlying uniform distribution here. But actually, as we increase the number of values in each one of the sample draws that we pull from those underlying values, you can see here that the shape of the distribution is starting to go towards normal. And then as we go down here and we have 10 data points per sample draw, and then we take the mean value, you can see that this is turning into the shape of the normal distribution. So this is just a very practical demonstration of what's happening with the central limit theorem, but let's look at that in R and go over some specific examples. So I will make this code available to you if you would like. I'll put it up on Blackboard. We're going to be working with the rivers data set, which actually we've worked with before. So let's just look very quickly at what the river data set is. So it's the lengths of all major North American rivers. The data set contains 141 major rivers in North America as compiled by USGS, so the US Geological Survey, and the river lengths are measured in miles. Okay, and it's a vector containing these 141 observations, and the sources for the data are just down here. In demonstrating the central limit theorem, the point that we're trying to make is that even if your population is not normal, if you have a sufficiently large sample size, the distribution of your sample means will be normal, and that allows us to use some of those techniques that we have available with the normal distribution, which I'm going to emphasize through this lecture. Okay, so we now understand the rivers data set. Let's make a histogram of this. So actually, when you look at the frequency of the values, so the large majority of the rivers in North America are under 1,000 miles. You can see you've got over 80 which are below 500 miles. And you've got about 40 that are between 500 and 1,000 miles. And then you've got very few, essentially, which go all the way up here to these very large numbers. So you can see, actually, just looking at this distribution, that it's quite heavily skewed positively to the right here by these outliers. So let's just examine some of the statistics for this population. So let's look at the mean, or the mean value if we sample. The mean value if we sample is 591 miles. The median is 425. So this gives you another inclination that this is quite a heavily skewed set of data, because in a normally distributed data set, you would have the mean and the median being essentially the same number. And then when we look at the standard deviation, it's about 493 miles. So we can just examine the skewness by running this package from Moments for rivers, and you can see that the skew is 3.18. It's quite a large positive skew that we have here. Okay, so that's enough about the underlying distribution. I just want to emphasize that, I just wanted to emphasize here that the actual data that we're pulling these samples from essentially is not normally distributed. But let's take a sample of 5 rivers and calculate the sample mean, and then let's compare it to the population mean. So the population mean was this here. Population mean equals 591. So let's just run this. We're getting 635 as the first mean, 909. So you can see how much variation there is by just having a small number of sample points. 642, okay, that's not too bad. 555, 1,412. So this just gives you an example of how much variation there is when we're using these smaller amounts. Okay, so let's create a loop. So basically now we're able to say, right, we're going to pull 5 numbers from the distribution each time. So let me just emphasize, in fact, before I move on, exactly what the samples function does. So we were taking the mean of 5 numbers drawn from the population. So that's basically what's happening each time. If you look at the console just here, these 3 numbers, these 3 entities are being drawn. Sorry, 5 entities are being drawn, and we're taking the mean of those numbers. Okay, so just wanted to make sure that that was clear before we progressed. Okay, so now what we're going to do is generate these 10,000 samples. So we're going to create an empty vector just here, and then we're going to go through a loop. So we covered this previously in the other lab exercises. So for I in 1 to 10,000, so remember that I will take any number between 1 and 10,000, and this is the beginning point here, 1, and it's going to go all the way up to 10,000 essentially. So I will take in the first step 1, in the second step 2, in the third step 3, and each time we're going to pull a sample of 5 data points, and we're going to take the mean of it, and we're going to place it into SAM5 based on the row index. So this just basically means that, imagine here in Excel we have this empty vector like we have here, SAM5. When I takes the value of 1, it's just going to put the mean value here in row 1, and then when I takes the value 2, it's going to place the next mean value, which we have down here, in the row index 2, 319.2. Okay, and so on and so forth. So essentially we're going to fill that vector each time, which means eventually we're going to end up with a vector with ideally 10,000 individual data points, as we have here. SAM5 has got 1 to 10,000 data points, and then all of the numbers are stored just here in the global environment. Okay, so let's look at some of the statistics for those sample means that we just pulled. So if we look at the histogram, we can see that it's also quite positively skewed, as much like the population distribution. If we look at the mean value, we get 591. The median value, we get 540, and the skewness 1.3, so still quite positively skewed. Okay, so the point of this exercise now is that we're going to change the number of data points that we're going to sample at each individual draw. So you'll remember that we took 5 data points previously here. Now we're going to sample 10 data points, so twice as many, and we're going to put it into a vector called SAM10, as I've just done up here. And now we're going to look at the histogram. You can see that we're starting to get more of a normally distributed shape. Let's look at the mean value. We're getting 587, and the median. So the mean and the median are starting to be much closer together, which is indicating that we're moving towards normality. And the skewness has now dropped below 1. So basically, by increasing the number of sample data points that we're pulling on each draw and taking the mean of that value, the distribution that we obtain is starting to become much more normally distributed. Okay, so we took 5 data points, we took 10 data points, and now let's try this with 100 data points. So each time we take a sample, we're going to take 100 individual data points on the population, as we've done here. And then we're going to take the mean of them, put them in this SAM100 vector that we've got up here. Now let's look at the histogram. And straight away you can start to see that this is already looking much more normally distributed in comparison to the previous examples. So here still quite positively skewed, getting better, and then this final one we're looking almost like a normal distribution here. The mean value we got was 591, and the median was 592. So the mean and the median are pretty much sitting now on top of each other, which is a good indicator of normally distributed data. And the skewness it's actually dropped below 0. So that's indicating that it's slightly negatively skewed now. But the point is that the skewness is a much smaller number in comparison to the first value which we got, which was over 3. Okay, so I hope that that's helped to show you how, as we go from just 5 data points per sample draw to 10 data points per sample draw, and then finally to 100 data points per sample draw, in these 3 different loops, we're able to obtain a distribution which essentially is normally distributed and therefore allows us to use a range of techniques that are available to us when we know that the data are normally distributed. So, before we progress, I just need to go over the standard error of the mean with you. So, essentially, we're able to calculate the standard error of the mean based on this equation. So here we have sigma x bar. So we're able to obtain this via sigma over the square root of the number of samples that we have. And the reason why this is important is that as the sample size increases, the standard error of the mean decreases. So this is just a basic measure of sample error that we're able to then use later on when we're interested in, for example, estimating confidence intervals. So currently we're going to ignore certain characteristics of this estimation process, such as the finite population correction, but it is just briefly mentioned within the book. So I just wanted to point that out. Okay, so let me just summarize, because there's been a lot of content there, and I appreciate it's new content and it's quite complicated. We have gone over the central limit theorem, and essentially we've identified that there are 3 principles associated with the central limit theorem that is very useful for then how we derive statistical metrics, which we'll be covering later in this class. We covered some of that in our calculations to show you how some of these properties play out. What's important though is I think you need to learn exactly what these principles are. So I'd like you please to read the chapter in the book, McGrew et al., but also the blowout box that's on page 118 in the book. So it's just here, and I've summarized it. I've summarized this content just here. The point that there are essentially 3 principles in the central limit theorem. So the frequency distribution of the sample means that we pull from the population data have a mean equal to the population. That's the first principle that we rely on in order to use sampling to represent the population. The second, as we've already shown in the R calculations, is that the frequency distribution of the sample means will be normally distributed. And thirdly, the frequency distribution of sample means will have a standard deviation equal to the standard error of the mean. So I brushed over that very briefly here, but that's the point that I was trying to emphasize. We need this equation because we might not always have the standard deviation, but we are potentially able to estimate the standard error of the mean. Okay, so these rules apply to the distribution of the sample means and not necessarily to the distribution of other sample statistics. Today we're just focusing on the sample means. And actually for a lot of the techniques that we will cover in the rest of the course, we will also be focusing on the mean of those samples that are pulled. So there's a lot of information there. Please take time to read what's in the book, go back over this video if it's not clear, and then look at any content on YouTube or other places that might help to support your understanding of this. And then if there's any issues, come back to me and say, Ed, I just don't understand X, Y, or Z, and I'll try my best to support you through that process. So confidence intervals, this is about how confident we are within an estimate which maybe we've made. So let's just define what we mean by confidence interval. So this is an estimate of a range of a range actually computed from observed data. So this is sample data, for example, and it proposes a range of plausible values for an unknown parameter that we want to estimate, and then hopefully generalize to the population. So let's just assume that this is the mean. And the proposed interval has a certain level of confidence associated with it and is based on the true value falling within this specific range. We do have some definitions before we continue, and I just need to introduce this idea of significance level. This is going to be really important as we move towards those inferential statistical techniques where we start trying to evaluate different hypotheses. So the significance level refers to the probability that the interval does not include the true population mean. And it relates to the strength of the evidence, which allows you to then reject the null hypothesis. So I'll get into this later, but for now we just need to know that the significance level is alpha. And essentially, alpha is set differently depending on the discipline which you're in, but it relates to the probability that the value you obtain does not include. So the interval that you obtain does not include the true population mean, as stated here. And then the confidence level, you'll notice that it's actually the complement of the significance level. And that's because here we have 100% of the data values which we collected. And the significance level here, for example, if we assume it's 10%, that means that 10% divided by 2, because you could be both below the mean or above the mean, means that it's 5% in each tail, at each end of the distribution. And therefore, if this is a 10% overall, that means that the confidence level is going to end up being 1 minus 0.1, so it's 0.9, so it's 90%. And this refers to the probability that the interval does contain the true population mean. Okay, so please learn those definitions. We're going to have to come back to them, and they'll be important for how we move forward with the content in this course, because we're going to need to go over significance testing in quite a lot of detail. I think we have maybe 4 or 5 classes left this term, which focus on using this particular technique. So common confidence levels, I did just emphasize there that this depends very much on the discipline which you're in. So those disciplines, maybe in the health sciences, may use different confidence levels because there are potentially more negative outcomes associated with the decisions which they might make through the statistics which are derived. So, for example, if you're going to administer a treatment on someone, and that treatment could save someone's life but also could cause them long-term health effects, then you might have you might require a different level of confidence than in other subjects, where if you got a false positive, or if you had a wrong result in some way, shape, or form, there might be less severe outcomes, essentially. So anyway, higher confidence levels result in wider confidence intervals. Essentially that produces less precise estimates because you've got a larger range of values, but it also reduces sampling error. So you're able to capture the true value of that metric, ideally. So I've just emphasized down here how our confidence interval is essentially the reciprocal of the significance level. So you can see here we've got alpha values ranging from 0.2 down to 0.01, and the width starts to change quite significantly of our confidence interval as we move to really quite small significance levels. So this is important. We will be picking this up at other points. So this looks really scary, and it's not. So I just want to work through this very slowly with you. This looks like a really big, scary equation, but let's just break it down, okay? So why don't I cover part of this up for now, just so that you're not quite so scared by what you see. Right, so for example, what we're going to focus on is how we calculate the upper confidence bound given a set of information, okay? And let's do this down here as well. So to calculate the upper confidence bound, we use this equation here, and that is essentially x bar, so the mean, the sample mean here, and then depending on whether it's you know, if you're looking in the top half of the distribution or the bottom half of the distribution, you would either plus or minus the remaining values. Let's just assume, as we're focusing on the top half of the distribution here, we're going to focus on adding these values, and then you need to add this the result of the z-score multiplied by the standard error, so sigma over the square root of n. So this equation we've already been through basically in the previous slides. You remember this is the standard error here, this is the z-score, and this is the sample mean. So each of these individual parameters we have worked out how to calculate, and we've spent quite a bit of time working out what they mean individually. Here we're just combining them in order to try and calculate a range. And the reason why I broke it into two parts is obviously you're going to have a lower bound beneath the mean, and you're going to have an upper bound above the mean. And just for simplicity now, we're going to focus on the upper bound. So what this is saying is, get me the upper bound, which is above or equal to this value here, which is the mean. So I don't think that there's anything here that we haven't already gone over. So we've gone over z values. I'm going to pick that up very quickly in a second. The population standard deviation, we know how to calculate. The sample size, n, so we've been over that many times. And the level of confidence, so for the interval, it's 1 minus the significance value, the alpha, which gives us the level of confidence that we're interested in. And that's essentially how you calculate the upper bound. So we're going to do that in an example, but let's just quickly kill those text boxes. So essentially what we're saying here when we look at the whole equation is that we're able to capture this lower bound here, the lower limit, and this upper limit here. And that within this, because we're interested in, say, a 90% confidence interval, 90% of the values fall here, and then only 5% fall at either end of the tail of the distribution. Okay, so that's quite high level. Come back to this in the future slides when we start to calculate these manually. If you're not sure of what's going on, particularly this, we will be returning to. Okay, so defining areas of significance and confidence. Well, we've kind of covered this already in the previous in the previous slide. So essentially, the significance is in the tail, so these parts here, and the confidence is those values surrounding the mean, essentially. So if we're interested in 90% confidence, it's this interval here from plus 165 standard deviations around the mean to minus 165 standard deviations around the mean. And what's important is that these values here, 1.65 and minus 1.65, well, they're Z scores. So essentially you can calculate these via the standardized tables in the back of the book that we covered in the previous probability sections. So if that's not clear to you, then please take a look at that again. So I'll just cover that quickly now. So we covered the statistics tables in the back of the book. What's important about these statistics tables is that it represents those values between the mean, 0 here, and the z-score, which is just representing half of the distribution. Okay, so you need to remember whether you're looking for all of the distribution or just part of it. I think the important point is that here we're interested in, for example, this distance, so 0.45, where 45% of the values lie. And actually, if we look in the Z table specifically to that value, 4505, so 0.45, here we're able to see it corresponds to a Z score of 1.6 on the y-axis and 0.05 on the x-axis, which means that 1.65 produces 1.65 standard deviations from the mean captures 45% of the data. So that's essentially how you need to think of this. You've got these diagrams now. It's going to be critical that we understand this concept. So if you don't understand the Z score or the number of standard deviations around the mean, then you need to put some effort into understanding this and reach out to me if you're really stuck. So let me just give you a visualization, and hopefully that will help you understand. So this image shows the true distribution at the bottom here. So it's this part. So this is the distribution of mean values. We have 10 sample means here. So these are the sample means x1, x2, sorry, x bar 1, x bar 2, x bar 3, x bar 4, so on and so forth up to x bar 10. Now, each sample mean has a 90% confidence interval, and that's what this range is here. It's saying that this is the 90% confidence interval for this one set of samples drawn from the population. Due to randomness, each sample mean is different. So you can see that that's quite a bit of variability there. But by building a 90% confidence interval around each one, only 1 in 10 samples therefore is likely to be in the tail. So when we actually look at the mean here, x bar 5 is the only one out of all of those draws which sits in the tail. So it sits in the extremes. Whereas the majority of the actual x bar values sit in the main part of the distribution. So when we think of this normal distribution bell-shaped curve like this, you need to remember that underneath it are all of those sample draws that we're pulling from the population. Often we can't always use the normal distribution, and we'll get more into this later in the term, but if we can't assume a normal distribution, for example, because the sample size is very small, then we'll need to use different distribution, particularly one called the t distribution, which in reality you might not use very often in practice, but it's really important for us just to at least point to this distribution in this work, as the lectures are here to provide the theoretical overview for the statistical content which we're going to be covering. So the t-value requires the number of degrees of freedom, and this is just a diagram here to emphasize how this distribution slightly differs from the normal distribution, which is in blue, and then we have the t distribution for different values in green, essentially. So we won't emphasize this too much yet, but I just need to point out to you that if you have fewer than 30 values, you might need to consider using different distribution, because we can't assume normality. And so far we've focused on trying to get the interval around points. You might want the interval around a proportion. So this is emphasized in the book. I'm not going to spend too much time on it now, but you can at least look at the math. So we can get a proportion essentially by dividing the proportion of the values with the specified characteristic by the number of values within our sample. So for example, if we have 20 values with a specific characteristic and there's 100 values in a sample, the proportion of data would be 0.2, so 20% of the overall values. And then once we have that value of p, we're able to calculate the confidence interval around it. And you can look in detail at how you do this, but essentially you need to take the z-score and multiply it by the the square root of p multiplied by 1 minus p over the number of degrees of freedom. Okay, so I'm not going to go through this in too much detail. I'm not going to provide you with a specific example now, but if you really needed to, you would be able to work through mathematically, given what we've already done, to work out this confidence interval. Okay, so let's produce an example. So a biogeographer weighed a random sample of 30 hedgehogs. She found that the mean weight of the sample was 0.885 kilograms and the standard deviation was 0.096 kilograms. Find the 90% confidence interval for the mean of the entire population of hedgehogs. Okay, so what we're given here is the mean value, 0.885, the standard deviation, 0.096 kilograms, the number of samples, which is 30 hedgehogs, and then we're given the significance level and the confidence interval, which is 10% and 90% respectively. What we want to do is calculate the bound around this. Okay, so let's just start with the upper bound, and this looks really scary, but it's literally just the equation which I emphasized before, which is just stated here for how we get the bound, and that's to take the sample mean and multiply it, and add or subtract the z-score multiplied by the standard error. Okay, so this is the standard error that we have here, which is a sigma, so it's the standard deviation divided by the square root of the number of samples. That's how we get the standard error. And then we need to get the z-score, so that's going to be dependent on the confidence interval that we define ourselves, for example. So here it's 90%. And we're already given the mean value for this particular sample. So let's work through this. So we have 0.885, which represents the mean. So that's x bar. To get the upper bound, we need to add the z-score multiplied by the standard error. So that's the standard deviation here, which is 0.096 divided by the square root of the number of samples, which is 30. So I hope that this first value is clear to you, the mean. This second part here is clear to you because it's the standard error. And the only part that I need to therefore describe is Y165. And you will remember that we looked up the z-score in the table at the back of the book. So for example, let's look at the distribution here. What we're saying when we say a 90% confidence interval is we want to capture all of the values that sit in this part of the distribution between the lower limit and the upper limit. But it means that we need to work out where this lower and upper limit actually is in relation to the rest of the distribution. So we know that 0.45, so 45% of the values will, as a consequence, sit between the mean and the upper limit. So that's where we need to go back to our z-scores. So 0.45, we found it just here, and it was 1.65 based on the values that we had. So 1.65 standard deviations above the mean in this case, as we were looking over here at the upper limit. So then when we plug that in and we actually do the math to produce what is 0.9138 for the upper bound, we're able to do the same for the lower bound, which is 0.8561. The difference this time obviously is that we're subtracting that amount because we got the upper limit first, and then for the lower limit we need to therefore subtract it from the mean. And when we put these together, what we're essentially saying here is that x bar, the mean, is above or equal to 0.856 and then below or equal to 0.914 based on that 90% confidence interval that we exogenously set at the outset in the question. So we said we want to be 90% confident of estimating that the value falls within this parameter range. Okay, I hope that's clear. If it's not, then rewatch the video and think again about how we basically fill out this equation that we've got here on the right hand side. So let's move on. Let's go to sample size estimation. And the question is, well, how many samples do you need for a specific confidence level? And so far, what we've essentially been doing is creating a confidence interval for data which we went out and collected ourselves. And then the question is, well, actually, can we determine what the sample size should be before we go out and collect the data? And that's really important because maybe we want to optimize the time and resources available to us, and therefore what we want is the minimum sample size that allows us to robustly make an estimate of what we think the population parameters are, but while simultaneously minimizing the time and resources that we spend. So that's what we're going to do in this section of the lecture. So this looks scary, but it really isn't. So essentially we're able to rearrange the equation that we were working with earlier in order to get the total number of samples. So you remember that we had the standard error and the z-score, and that was able to produce an error for us, so the allowable amount of error. Essentially, we're able to rearrange this equation in order to get n on the left-hand side and the other variables on the right-hand side, and therefore we're able to estimate how many samples we would need to make an estimate based on the acceptable amount of error we're comfortable to live with. So for the mean value, what we can do is we can move here from this error equation to firstly removing the square root. So you'll see here in the standard error, the number of samples we're taking the square root of that. Well, we can remove that essentially by raising all of the other values to their square. Okay, so that's step one. Then in step two, what we want to do is we want to move n, which is the value that we want to find, over to the left-hand side of the equation. So we're able to do that as demonstrated here. And then finally, what we want to be able to do is we want to move the e squared value, which we have, over to the right-hand side of the equation. And we're able to rearrange it as so. So basically, if we take the square root of the z-score multiplied by the standard deviation divided by the error, that will find the number of samples that we need to meet that error value. Okay. So that looks really big and scary, but it's not. What we're going to do is take this equation here, and now we're going to work that out for a particular example. So the equation on the prior slide needs the population standard deviation, which is probably unknown in reality. But we are able to substitute a sample standard deviation in, so we can either do that from previous studies, making an educated guess, or doing a pretest or preliminary sample. If you're doing a pretest, then you probably want to do a two-stage sample design and reuse the samples that you actually obtain in the first step. So we're able to look at how we would do this now. So if 50 total samples are needed, return to the population and collect 20 more to add to the original 30 that you collected. Okay, so we start with 30, we need 50 in total. We're able to basically do the first tranche of the data collection and then do these estimates and then return and collect the remaining estimates that we think we need in order to be reasonably robust in the estimates that we produce. So suppose you want to estimate the mean yield of corn per acre to a confidence level of 95%. So a preliminary sample of 50 acres found that the mean to be essentially 74 bushels, and with a standard deviation of 16.65 bushels. Now, I didn't know what a bushel was. Maybe that's because I use metric units. So this would be measured in kilograms in the UK. So I had to go and look this up, but it's an imperial measurement of units, essentially. So apologies if you knew this. I didn't know it, and therefore had to go and look it up. But essentially, what we're doing here is we're doing the math. We're trying to estimate these values. The examples are just here to help us understand how to use the equations that we produce. So you know, this is probably quite abstract in comparison to the real examples that we would use in reality. I think generally, as you move towards the harder science subjects, most people aren't using imperial measurements anymore. They're going straight to metric measurements, and that's because you've got the benefit of having a decimal system, and there's a lot of benefits with that. I really need to share that video with you of one of the NASA crashes where unfortunately, I think it was one of the rocket launches, they'd had to convert between metric and imperial, and there was a mistake along the way essentially, and it led to a crash. So it was a very expensive crash. I don't think anyone was injured in it, but I'll need to share it with you again. I'll share that video with you. So if you can use metric units, I would definitely advise that you do that because it helps to reduce the likelihood of getting a wrong answer, introducing a mistake. Okay, so going back to the example, we want to estimate the mean yield of corn per acre to a certain confidence interval, and we're given the number of samples, preliminary taken, the mean value, and the standard deviation. Okay, so how many acres do we therefore need to sample in order to be within 3 bushels of the true mean? So we're given a lot of data. We've got the standard deviation here. We've got the error that we're willing to accept. We've got the confidence interval that we've exogenously defined. So we just say we want this to be within 95%. We want to be 95% confident that we've got the right answer. And then I've just placed here the equation from the previous slide where we rearranged the error estimation part so that we could basically get the number of samples required. And what we're able to do is to take the z-score, which in this case is 1.96. So for a z-score of 0.95, so that's where 95% of that's where we want to capture 95% of the values. We basically have a z-score for half of the distribution of 0.475, so this number just here. So to get that 1.96 value, we're going to look for the 0.475, 0.475. Here we go, this is where we are. So it's 1.9 on the y-axis and 0.06 on the x-axis. So we get 1.96 to capture that, that amount of, that proportion of data values between the mean and the upper limit. So we know that this upper limit value here is 1.96 standard deviations above the mean. Okay, so I hope that that's clear. I've worked through both of those z-scores that we've captured for the 90% and the 95% values. In reality, you just need to learn them and just know what proportion of the data are represented at those specific z-score values, and please do that for the 90 and 95 percentile marks because you will be asked them in an exam. Okay, so that's how we get this value here, 1.96 for the z-score. And then for this value here, sigma, which is the standard deviation, we've got 16.65, and we're going to divide it by the acceptable error margin, which is within 3 bushels of the true mean. So when we plug that into the equation, the most simple form here, we want to multiply these in the numerator by the denominator, and then basically we raise that answer to the power of 2. So we take the square of it, and that produces 118.32 acres, because we're interested in how many acres we need to sample in order to be within 3 bushels of the true mean. Okay, well, we've already sampled 50 acres in our preliminary study. So essentially what we need to do is we need to subtract those 50 acres from the 118.3265 acres that were estimated here, and that results in 68.3265. What's important is that you could sample part of an acre, but the point is that here, in this case, we're going to round up. we don't want to round down, because ultimately, if you round down, then you wouldn't be you would be incorrectly you basically would. It's better to overestimate. It's better to be overly rigorous in your estimation than it is to be uh, under rigorous, essentially. So the point is that I mentioned before, if there are negative outcomes from getting this wrong, you really want to avoid them. So that's why you're better off rounding this up so that you get the answer 69 acres. So when you work through the math here, this is how you're able to produce this answer for the question which we set. Okay, so I hope that that's clear. If it's not, relook at the question and rewatch the video. We're going to be going over this content within the R lab, and I'll then be setting a test on it. So please make sure that you get the lab work completed and that you do the test. And I think that that will put you in a good place for both progressing with the rest of the course content, but also with preparing for the future exams that we're going to have. Okay, great. Well, I hope that that was interesting for you. I do appreciate that it's a lot of material, and also that you know, it's quite hard material. It's challenging. I do appreciate that. So please reach out to me if you're stuck, if you've got any questions, and I'll look forward to seeing you all soon. So thank you very much for tuning into Lecture 7. Goodbye.